The next law I want to talk about is about conservation of momentum. Conservation of momentum is probably, it's not the most important, but it's very important. It actually comes about from Newton's laws, Newton's second law and Newton's third law in particular. When we talk about momentum, we're primarily talking about collisions and explosions. You will use momentum typically to solve any kind of problem that deals with those situations. There are different types of momentum, but collisions, not momentums. There's different types of collisions, but we won't talk about that until we talk about energy. Okay, but first of all, conservation of momentum. Now, talking about a collision, we have two cars that collide with each other, right? And let's say, for simplicity's sake, that both of these cars have identical mass values, and they have relatively the same velocities. Okay, conservation of momentum says that whatever momentum I start off with, I end up with. But why? Why is that true? Well, in the case of a collision, I have a car striking another car. That car is delivering a force on that car. Okay? So in the process of the collision, this car slams into that car, and there's a force being exerted on that car. Okay? Now, looking back at Newton's third law, what does that mean? If this car exerts a force on this car, what else do we know? Well, we know forces are in pairs, and that they're acting on two objects, and that they're the exact same magnitude. So if I exert a big force on this car 1, let's call this car 1, then looking at car 2, I have to exert the exact same type of force, the exact same magnitude of force, but in opposite direction. So car 1 gets slammed into by car 2 and experiences this force. Well, car 2 experiences the exact same force back. It's the exact same magnitude, just in an opposite direction. That's Newton's third law. That has to be true. If it's not true, then why would we call it a law? Okay? So, car slams into this car. Car 2 hits car 1. It experiences this much force. That means, in return, car 2 experiences the exact same size, the exact same type, just in an opposite direction. That's Newton's third law. Now, going back to conservation of momentum, well, this car hits this car. This car, in turn, hits back, right? But if this car hits this car, does it take longer in the collision for this car to hit this car than it does for car 1 to hit back on car 2? So, what I'm asking, I'm going to reiterate this, the amount of time that it takes for car 2 to hit car 1, is it less than, equal to, or greater than the amount of time that is required for car 1, or the amount of time it takes for car 1 to hit back on car 2? Now, hopefully you see it's the exact same amount of time. Boom, they collide. They should experience the exact same amount of time during that collision, because it's one car collapsing into another car. It's the exact same time. So we can say that they both experience the same force and both experience the exact same amount of time for that collision. Now, I'm not necessarily talking about a person inside that car. I'm talking about the car in general. Okay, so the person inside the car can experience a longer period of collision, but that's another story. That would be the person and the airbag colliding. It's not the car on car. Okay, so this one's experiencing force in this direction times time. This one is experiencing force in this direction times time. So in both cases, they're experiencing a change in momentum. Going back to the idea of impulse, which we got from Newton's second law. So in both cases, they're experiencing a change in momentum. Well, not only are they both experiencing a change in momentum, they're experiencing the exact same change in momentum. The exact same force, the exact same time. Exact same force, exact same time. The exact same changes in momentum, right? But there's one difference. This one is in this direction. This one is in this direction. Okay? So this one gains momentum in this direction. This one gains momentum in this direction. If I were to add the gains in momentum from these cars, remembering that I'm adding them as a vector, so there's a direction dependence, what I end up with is 0. There's no net gain in momentum. This one gained so much in this way, like 5 units. This one gained the exact same 5 units, but in the opposite direction. If we talked about coordinates, this is a positive change in momentum. This is a negative change in momentum. So looking on the x-axis, let me move over a little bit here, that one gains positive momentum, one gains negative momentum. So when I add the positive to the negative, I get 0. It's 0. It is always 0. The only way that it's not going to be 0, that the conservation of momentum doesn't apply, is if there's another car or another rock or a jet engine or something else that we're not accounting for. This car bangs into the other car, but we forget to consider that there's a piston on the bottom of the car to throw it up, or there's a jet engine to push it into the ground, or anything else that we just simply haven't accounted for. If we account for everything that's going on, the Earth, the moon, the jet engine, the piston, whatever, then momentum is always conserved. Okay? So the truth of the matter is momentum is always conserved. We just have to make the system big enough to take into account everything that's going around. Okay? So the only times that momentum is not conserved, if we ignored something there, or we forgot to include this force or that force into the system. As soon as we do that, it's conserved. So we say that momentum is conserved barring any external forces, which means that we're not including those outside forces, things that we haven't accounted for. Okay? So those are the only situations where momentum is not conserved. Cool? Conservation of momentum, a really cool idea. Alright? Thank you.